Okay. So if we write down the likelihood using the normal distribution, then it turns out like this, where we have the y minus x beta norm square term again.
Okay.
So the point is that if we, so first, the comment is that sigma square can be known, either known or unknown, right?
Okay.
Now, if it's known, then beta is the only unknown in this equation.
Oh, whoa,
If
whoa,
it's,
whoa, whoa. Where, how did, whoa, wait, sorry. This just one, how did we get X beta here? How did we get that there?
if you write down the normal distribution, probability distribution, this is what you get. Uh, Let me show you why. So expectation of y will be x beta. Do you agree to this?
No, I mean, not that I don't agree. How did you get that?
Okay.
I,
So we assuming, yeah, let's derive that. So we are saying that expectation of epsilon is 0. Sorry.
expectation of epsilon is 0. Okay, I'm with you.
That's my assumption.
Yes.
And variance of epsilon is sigma square times identity matrix.
Wow.
Because we are
Okay,
assuming,
so now we're okay. This is
okay.
interesting. Okay. Now we're what we're doing is we're taking what we did with the probability, but we're doing it in matrix form now, is pretty much
Yes, we are just writing those results in matrix form. Because
interesting.
epsilon is a vector now, its a covariance matrix,
Epsilon is
covariance thing is a
vector.
matrix. So that
Yes,
is sigma square times identity.
got
Okay.
it. Okay, great.
And then we know that y equals x beta plus epsilon.
Yes.
And we know the mean and variance of epsilon, so we can find the mean and variance for y.
Got it.
The mean will be added at the x beta term, and the variance will remain unchanged.
Oh my gosh. Okay. I got it. I'm with you.
Okay.
Sorry. Yes.
Okay. So I'll just write down variance of y is sigma square identity.
Okay.
Okay. And then because of this, if you write down the multivariate normal density,
Okay.
this is what you get,
Perfect.
y minus x beta. So x minus mu whole squared.
Okay.
Okay. Now the point is, if you fix the sigma, then maximizing this quantity is same as minimizing this quantity, the y minus x beta norm square.
Can you say that again? Sorry.
For a fixed value of sigma,
Okay.
maximizing the L
Yeah.
is same as minimizing this y minus x beta norm square.
Okay. Perfect. Yes.
Okay, because nothing else is varying in this.
Yes. Okay.
Okay, so MLE for beta is same as the beta that you already get, beta least squares. Okay, so we have the same formula.
Okay.
There are two differences. One is now we can talk about the beta hat as a random variable because we have probability now. We didn't have probability earlier.
Okay.
And second thing is we can estimate sigma also.
So Jay, I'm gonna be honest.
Yeah.
I think it's like I can conceptually see what you're saying and where you're going with this.
Yes.
I think
Yes.
I need to review some of like I need to bring back the I'm getting
Yeah.
confused
Yeah.
on the
So whichever steps you find it awkward or not, I would like to explain a bit better. So which part
up to
is
where
like,
you wrote, the likelihood formula, that up to there
yes.
makes sense. I guess
Okay.
I'm getting confused on like when you're like the maximizing the likelihood is this.
Yeah. So what
Okay,
I'm saying is,
I
okay, let's do
understand
that
that.
step by step.
Okay.
You have an expression for L. We want to maximize this.
Yes.
And we are saying that the sigma is constant for now.
Okay.
Okay. So then this term constant outside doesn't matter. We only have exponential of something.
Yes. Okay.
Okay. Now this is exponential of a negative thing.
Yes. Okay.
So if I have to maximize L, I have to minimize this negative thing inside the exponential.
Okay.
And then again, the 1 by 2 sigma square can be ignored because it is a constant.
Okay.
So that means I have to minimize this y minus x beta norm square.
That makes sense. That makes sense.
Okay.
Okay.
So that's what I'm saying, that maximizing the L is same as minimizing this is sum of squares of letters.
Got it. Okay. So that sentence
Okay.
makes sense.
Yes. Now we have already done the algebra of how to do minimizing of y minus x beta, the sum of squares of errors. So the answer that we got here, so people write it as beta ls. We should get the same answer for MLE as well.
Oh, okay. Okay. Yes. There's just another method. Okay.
Okay, makes
Got it.
sense?
Yes.
Okay. So I'm saying what is extra for MLE is there are two things. One is we can estimate the sigma also because sigma is another parameter. So if sigma is not given in the model, like sigma is an unknown parameter in the model, we can estimate it. And the second thing is we can talk about probability distributions of the beta hat, the estimated beta. Okay. So we want to make comments about how good our estimated beta is. Can we do better? And that's where all those Reach and Lasso and all those will come into picture. Like we want to understand in what situations the least squares method will not work well or MLE method will not work well.
Okay.
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 Now, what we will do here is, first of all, we have the expression for beta hat, which is beta ls, which is this one. So I'll just copy this. And then I'll try to take expectation of this. Okay.
Okay.
So in the expectation, the first part, this is x transpose x whole inverse x transpose is all constant.
Right.
So I'll just put as is. And then I have to take expectation of y.
Why? Okay.
So expression of y, we have already derived expression of y is x beta. So I'll write x beta.
Okay.
Okay. I
Yeah.
mean, nothing surprising, right?
No.
It's just algebra. I mean, some of the algebra might look daunting, but it's just algebra.
Yes.
Now, again, some magic will happen. You see, you have an x transpose x whole inverse, and right after that, another x transpose x. So this will cancel.
Okay. So the
And
expect.
we're left with beta.
Okay.
Okay. So all that formula looks so complicated, but if you try to take expectation, like all that cancels out and you get expectation of beta is beta.
So now the algebra makes sense, but I don't understand
Yes.
what that means though. What does that mean?
That means that the beta estimator that we have, which is unbiased, on an average, it will target the correct beta.
Got it. Okay.
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 And we are also supposed to derive the variance of beta ls. I won't do the algebra here. I'll just write down the formula. It is sigma square, and then you have this x transpose x thing coming again and again, and then whole ellipse. Okay. And you can also find a expression for the sigma square. So estimator for sigma square is SSC. Again, like the way to derive this is take this expression for likelihood, take a logarithm, then take a derivative and set to the derivative to 0. Then you
That's
get
the
this,
MLE method, right? Yeah.
the MLE method. So these are the two most important results, that the beta hat is unbiased. It has this expression for variance, and the sigma square estimator exists. Now, since we did SVD earlier, I will try to use that quickly. So we derived that x transpose x is q, x transpose whole inverse is q d power minus 2 q transpose, right?
Mm-hmm.
So let's substitute it there. So far everything is algebra. We haven't like said what's the meaning and what's the point of doing all this. Now we'll get some point. So this, right?
Mm-hmm.
And I have a
Squared in the front.
sigma square at the front. Now we can make some actual comments about how good or bad estimator this is. So if your estimator has 0 bias, that means on an average you are targeting the correct thing. So then what you want is the variance to be low. If the variance is high, that means you will be away by a lot of amount. But if the variance is low, that means you will be very close to it. So we want the variance of beta hat to be low. Now, in this expression for variance, the first term is sigma square, which we cannot control. And then Q and Q transpose appears. But remember, these are just rotation matrices. So this is like just like a change of basis. They don't really like change much. They just rotate the picture in a suitable dimension rather than the response and the regressor variable that you are familiar with. It is thinking in terms of some other coordinate system. The
Okay.
important part is this d power minus 2. Okay. Now d power minus 2 means that I had a diagonal matrix D of the singular values. And then individually, all the diagonal elements, I'm doing 1 by d1 square, 1 by d2 square, and so on.
Okay.
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 Now, if one of the di's is very large, let's say 100, then 1 by d square will be 1 over 10,000, right?
Small.
That's very small,
Right.
which means that the variance is very small,
Right.
corresponding in that coordinate.
Okay.
Okay. So that's a very good thing for us.
Yes, exactly.
So large singular values
I mean, that's a good
are good.
estimator for.
Yeah, that's a good estimator.
Yeah, because variance
Will be low.
will be low.
But on the other direction, small singular values, so close to zero singular values are very problem. Because let's say you have a singular value of 0.01, then it will be 1 by that square, which will be 10,000. So like really large errors.
Right.
So small singular errors are bad.
Super cool.
Okay. And all the remaining theory of penalized least squares and all those things, lasso, ridge and all, is just different ways of correcting this.
Okay.
Okay. So maybe we can do one today and then leave the other.
Yes, can we pause here? Actually, Sujay, can we just, I
Okay.
think this is a really good spot. I want to review all of this week then too. He's gonna
Okay, sure.
he's gonna teach linear regression and stuff starting on, we don't have class tomorrow, so Wednesday. So I'll
Okay.
let you know. Maybe I'll send you a message on Thursday or Friday and let you know what he teaches and everything like that. And we can
Okay.
maybe like go from there. What do you, maybe Ridge would maybe be the next discussion?
Yeah, ridge would be the next steps to try.
This is
Ridge and then lasso and then Bayesian. These three things I want to cover, and all three are related.
Bayesian is regression, also Bayesian regression.
Yeah, there is a Bayesian regression also.
Bayesian regression.
And this is related to ridge. So like they relate to each other.
Yeah. Okay. Okay. Okay, buddy. I appreciate this. This is super helpful.